Summer of 1944. The war in Western Europe had entered a new, relentless rhythm. The Allied breakout from Normandy was spreading like a tide across the French countryside, and the German High Command had one order for every retreating unit: destroy every bridge. From Brittany to the Loire, from the Seine to the Meuse, demolition teams of the Wehrmacht and the organization Todt worked day and night to cripple the advancing enemy. They placed charges beneath the arches, weakened supports, and dropped spans into the rivers, turning the waterways of France into natural fortresses. To the German engineers, this was methodical science. The same precision that had built the Autobahn was now being used to tear it apart. In late August, as American armored divisions of the Third Army pushed south of Le Mans toward the Loire, a group of German engineers watched the sky turn orange above the town of Tours. They had blown the bridge only hours earlier. The river was clogged with debris, broken timber, and twisted iron beams. The engineers were confident that no army could cross this quickly. The Americans would need ferries, heavy cranes, and days of repair before even a single truck could pass. That delay, even just a few days, could buy the German command time to establish new defensive lines along the Seine. But by the following morning, the impossible had happened. From the opposite bank came the rumble of engines, first scattered, then continuous. Across the mist-covered water stood a new structure, a bridge that had not existed the night before. It was not made of stone or concrete, but of thin metal panels arranged with mathematical precision. Trucks rolled over it, followed by jeeps, half-tracks, and tanks. To the German observers, it seemed like a mirage born from exhaustion. They could not comprehend how an entire armored column was crossing a river that had been impassable less than 12 hours earlier. What the Germans did not yet know was that this was the result of a new kind of warfare, industrial engineering adapted for the battlefield. American combat engineers, equipped with prefabricated Bailey Bridge panels, had arrived within hours of the demolition. They worked through the night with floodlights covered by red filters to avoid detection from the air. Under the supervision of officers trained in England, they unloaded steel sections from GMC trucks, pinned them together by hand, and rolled the structure forward across floating pontoons anchored in the current. By dawn, a bridge capable of supporting tanks had emerged from the dark river. For the Wehrmacht, such speed defied logic. German bridge-building doctrine had emphasized precision and permanence, relying on heavy tools, cranes, and reinforced materials. In contrast, the Americans approached construction like assembly line manufacturing. Every beam, bolt, and joint had a number, every soldier knew his role, and the entire process moved with mechanical discipline. To the Axis engineers, watching from a distance, it was as if the United States had turned industrial mass production itself into a weapon of war. Reports from field observers spread quickly through the German ranks. Commanders in Orleans and Chartres received frantic messages that the enemy has crossed the Loire again. The same pattern repeated across France. Bridges destroyed by retreating forces were reassembled within a day. By early September, American units were advancing faster than their supply maps could be updated. For the engineers of the Reich, who had believed that rivers would halt the enemy for weeks, it was a revelation and a warning. The war had entered an era where destruction was no longer enough. Everywhere the Germans looked, the evidence contradicted their assumptions. The rivers that were meant to divide France now carried the momentum of an advancing army. Wooden piles were replaced by steel trusses, ruins were replaced by order. To those who witnessed it, the sight of a Bailey Bridge rising from smoke and rubble became more than an engineering miracle. It was the visible proof that the United States had mastered the logistics of speed. And as the war moved eastward, each new bridge reminded the Axis that time itself had become their most dangerous enemy. For the German High Command, the destruction of bridges had long been a cornerstone of defensive strategy. Since the early years of the war, the Wehrmacht had relied on a doctrine that viewed infrastructure as both a shield and a weapon. Rivers were natural barriers, and bridges were choke points, objects that could be sacrificed to halt an enemy's advance. When the Allied armies broke through in France during the summer of 1944, German engineers reverted to this familiar logic. As they retreated eastward, they destroyed every major crossing they could reach, the bridges over the Loire, the Seine, the Marne, and the Meuse. The goal was not victory, but delay. Every hour gained through demolition meant more time to regroup, to dig in, to build another defensive line. The strategy had precedent. In 1941 and 1942, the German army had used similar tactics in the Soviet Union, demolishing bridges to slow the Red Army's counterattacks. The assumption was simple: a modern army could not move faster than its logistics. Tanks without fuel, trucks without roads, and men without supplies were powerless. A blown bridge, therefore, could achieve what artillery could not: a pause in the enemy's momentum. German engineers believed that this principle would hold true against the Americans, whose mechanized divisions relied heavily on transport columns stretching for miles. If the bridges fell, the machine would stop. Yet the assumption contained a fatal flaw. The German approach to engineering was rooted in permanence. Their bridge construction units were trained to build for endurance: heavy steel trusses, concrete abutments, precise calculations, and standardized machinery. These methods required time, resources, and relative calm. When forced to destroy their own work, German engineers accepted that rebuilding such structures would take days, even weeks. They believed their adversaries operated under the same physical laws. What they failed to understand was that the American system had redefined the laws themselves. By 1944, the U.S. Army Corps of Engineers had embraced an industrial philosophy of war. Everything was modular, mobile, and replaceable. A bridge was no longer a fixed structure but a product, assembled from parts like a military vehicle or a factory machine. The British-designed Bailey Bridge, produced under American license, epitomized this shift. It could be built by hand, section by section, without cranes or welding equipment. What had once taken the Wehrmacht a week to construct, American engineers could accomplish overnight. This difference was not just mechanical, it was psychological. To German officers, the American method appeared reckless. The idea of assembling steel panels under fire, without surveying equipment or heavy tools, violated every principle of traditional military engineering. In their mindset, precision ensured safety, and speed invited collapse. But the Americans thrived in imperfection. Their systems were designed for chaos: bridges that flexed under load, beams that could be replaced mid-operation, crews that rotated seamlessly between tasks. In the industrial warfare of the 1940s, adaptability had become the new discipline. The result was a widening gap in tempo. Each time the Germans destroyed a bridge, they expected a lull in the fighting, a brief pause to reorganize. Instead, within hours, the sound of American engines returned. The rivers that were meant to stop the advance became mere inconveniences. Entire divisions crossed on structures assembled in the dark by men who treated construction like a form of combat. German reports from the retreat across France spoke of frustration and disbelief. The enemy crosses faster than we can destroy. This was the core of the problem, the clash between two philosophies of engineering. One side sought control through durability, the other sought control through momentum. The German army believed that mastery over materials would dictate the course of war. The Americans believed that mastery over time would. And in the summer of 1944, it became clear which vision the 20th century would favor. By 1943, the United States Army Corps of Engineers had undergone one of the most dramatic transformations in its history. In the early years of the war, American engineering units had been organized much like their predecessors from World War I, small, specialized detachments equipped with basic construction tools, wooden timbers, and limited mechanized support. Bridges were often built from local materials, a process that demanded time, skilled carpenters, and relative safety from enemy fire. But as the war expanded into multiple theaters, from the jungles of the Pacific to the deserts of North Africa, it became clear that this approach was unsustainable. The modern war demanded mobility, and mobility required an entirely new philosophy of engineering. The turning point came in 1942, when the United States entered into full industrial collaboration with Britain. Among the technologies transferred under the Lend-Lease program was a revolutionary design by a British civil engineer named Donald Bailey. His invention, the Bailey Bridge, had been tested by the British Army in 1941 and had already proven itself in North Africa and Italy. The design was deceptively simple, a modular bridge made of prefabricated steel panels, each 10 feet long and weighing around 570 kilograms. These panels could be joined with pins and bolts, no welding, no cranes, no precision machinery required. The bridge's strength came from its geometry. A series of interlocking trusses capable of supporting tanks and heavy trucks, yet light enough for soldiers to carry by hand. When American engineers first encountered the Bailey system, they recognized its potential immediately. The U.S. Army requested production rights, and by 1943, American factories in Pennsylvania, Michigan, and Illinois began turning out thousands of sets under license. Each complete bridge fit neatly into the standardized logistics system of the U.S. military. It could be loaded onto a convoy of 2.5-ton GMC trucks, delivered to the front, and assembled on site. The Bailey Bridge was not just an engineering marvel, it was an industrial product tailored to the rhythm of American warfare. Training became the next priority. Across Britain, U.S. engineer battalions prepared for the invasion of Europe at camps such as Chiseldon, Ripon, and Salisbury Plain. There, soldiers practiced constructing bridges in mud, rain, and darkness. Instructors insisted that teams work without light, using only touch and muscle memory to align the panels. Crews learned to anchor pontoons, drive pins under fire, and calculate spans by instinct. Speed was everything. In some units, bridge assembly was treated like a competitive drill. The record for a 120-foot span could be under 3 hours. By the spring of 1944, these men were among the most highly trained field engineers in the world. The Bailey Bridge fit perfectly into the U.S. Army's broader doctrine of mechanized warfare. The American approach valued standardization, mass production, and interchangeability, the same principles that defined its tanks, rifles, and vehicles. Each bridge component had a number and a place, allowing different units to assemble them interchangeably. The modular system also meant flexibility. Bridges could be extended, reinforced, or converted from floating to fixed structures as the tactical situation demanded. This adaptability would later prove decisive in France, where rivers and canals formed natural barriers that could otherwise have paralyzed an advancing army. By mid-1944, the U.S. Army possessed over 2,500 Bailey Bridge sets in the European theater of operations. The 79th Engineer Combat Battalion, the 1,104th Engineer Group, and dozens of others carried these components across the English Channel in preparation for the Normandy landings. When D-Day came, these units followed closely behind the 1st Infantry waves, ready to repair destroyed roads and crossings within hours. The Bailey Bridge became not just a tool but a symbol of a new kind of warfare, one where engineering and logistics could move as fast as the battle itself. The campaign in France in the summer of 1944 became the first great test of the Allied bridge-building revolution. When the Normandy landings succeeded and the breakout from Saint-Lô began in late July, the American Army's greatest challenge was no longer the German defense itself, but the terrain that lay ahead. Northern France was cut by hundreds of rivers and canals: the Orne, the Loire, the Seine, the Somme, and the Meuse, each of them a potential barrier that could slow an army of trucks, tanks, and artillery. The German retreating forces, following orders from the Oberkommando der Wehrmacht, demolished nearly every bridge as they fell back toward the east. The goal was to turn France's waterways into obstacles of steel and rubble, forcing the Allies into a logistical nightmare. For the U.S. Army engineers, this was the moment they had been preparing for since their training days in Britain. As the infantry and armor advanced, engineer battalions followed within hours, hauling Bailey Bridge components on convoys of GMC trucks. The system was designed for this pace. Each truck carried a numbered section, and every crew knew its role. The layout was executed with the same precision as a factory assembly line. When reconnaissance reported that a bridge had been destroyed, the engineers were already moving before the column even stopped. One of the earliest and most symbolic operations took place at the Orne River near Caen in August 1944. German engineers had demolished the existing bridge in an attempt to isolate British and American advances. The 79th Engineer Combat Battalion arrived at the site during the night, guided by faint red light lamps and the sound of the current. Within hours, the first Bailey panels were being laid across floating pontoons. By morning, a 180-foot Class 40 bridge stood where there had been only wreckage. The crossing reopened supply lines for the 21st Army Group and proved that the new system worked not only in theory but under fire. Similar scenes unfolded throughout the campaign. In late August, along the Seine near Mantes-Gassecourt, U.S. and British engineers built a series of Bailey bridges under constant artillery shelling, allowing Patton's Third Army to continue its rapid eastward advance. Near Rouen, the 1,104th Engineer Group constructed 3 bridges in less than 24 hours. The pattern was always the same: demolition at night, reconstruction by dawn. German field reports, intercepted later by Allied intelligence, described the phenomenon with frustration. The enemy restores his bridges faster than we can destroy them. Each successful operation deepened the Allies' momentum. Rivers that had once defined defensive lines now became milestones of progress. The Bailey Bridge transformed from a temporary measure into a strategic weapon. It allowed American forces to sustain their pace without waiting for permanent repairs or heavy machinery. Tanks that had been halted at riverbanks one day were already across the next. Supplies flowed forward in an unbroken stream. For the first time in modern warfare, logistics matched the speed of the offensive. To the German engineers observing these operations, the realization was unsettling. Their calculations, once rooted in predictability, no longer held true. They had assumed that time and geography were on their side, that rivers could buy them space to regroup. But the Allied engineers had rewritten the equation. By standardizing every component and drilling every motion, they had made bridge construction almost immune to delay. What had once been an engineering problem had become a matter of routine. The events in France became the catalyst that defined the remainder of the war's European campaign. The rapid bridge work over the Orne, the Seine, and later the Meuse and the Rhine, proved that Allied mobility could not be contained by destruction. The Germans could burn, mine, and demolish, but each act of sabotage was countered by methodical reconstruction. In the balance between destruction and creation, the advantage had shifted decisively. The engineers of the United States had turned rebuilding itself into a weapon, and in doing so, they changed the pace of modern war. The secret behind the Bailey Bridge's success lay in its design, a masterpiece of wartime standardization and simplicity. Every element of the structure had been conceived with the battlefield in mind, modular, repeatable, and entirely man-portable. Each steel panel measured 10 feet in length and 5 feet in height, weighing approximately 570 kilograms. It could be lifted and carried by 6 to 8 soldiers, connected to the next with heavy steel pins and secured by bolts. The entire assembly required no welding, no cranes, and no heavy machinery. The process was not only efficient but elegant in its logic. Where traditional bridges demanded skilled engineers and precise measurements, the Bailey system could be built by ordinary soldiers trained to follow a sequence, step by step, number by number. Every bridge was composed of standardized parts: panels, transoms, stringers, junction posts, and roadbed sections. The panels formed the side trusses, the transoms acted as crossbeams, the stringers carried the decking. Each part fit into the next like components on an assembly line. The entire system was based on interchangeability. Any panel could replace another, any bolt could fit any hole. This meant that even if parts were damaged in transport or combat, replacements could be pulled from other sets without delay. The philosophy was purely industrial. Mass production had finally entered the realm of field engineering. The construction process followed a clear rhythm refined through training and repetition. Once a river crossing site was secured, survey teams measured the span and current. Trucks carrying bridge components, usually 2.5-ton GMC cargo vehicles, lined up near the bank. Soldiers unloaded the panels by hand and laid them in order of assembly. The structure began on the shore as a flat, horizontal frame, each section pinned to the next. When the truss reached the required length, it was rolled forward over small steel rollers until it extended across the gap. The bridge quite literally launched itself a principle known as cantilever launching, using its own weight to balance as the far end reached the opposite bank. No cranes were needed. Instead, hand winches, ropes, and muscle power did the work. Crews labored through the night, often under artillery fire or air raids. The metallic clang of panels echoed across the rivers of France, mixed with shouted commands and the whine of bolts being driven into place. Floodlights were covered with red filters to conceal activity from enemy aircraft. The men worked in shifts, rotating every few hours, guided by instinct more than sight. Many engineers described the process as mechanical teamwork, each movement synchronized, each soldier aware of the next step. The modularity of the Bailey Bridge allowed engineers to adapt to every tactical situation. Depending on the weight the bridge needed to support, panels could be stacked in double or triple configurations. Double single, double double, or even triple triple. These reinforced versions could carry up to 70 tons, enough for a fully loaded Sherman tank or a convoy of heavy trucks. If the ground was unstable, pontoons or barges provided floating support. In urban areas, bridges could be anchored to the ruins of destroyed structures. The design's flexibility meant that geography ceased to be an obstacle. Speed was the defining element. A well-trained combat engineer company could construct a 120-foot Bailey Bridge in less than 8 hours, even under fire. Records from the 291st Engineer Combat Battalion during the advance to the Rhine show entire crossings completed overnight, allowing tanks to pass before sunrise. On average, a single engineer battalion could transport and assemble more than 300 tons of bridge components in one operation. In practice, this meant that the U.S. Army's advance was limited not by destruction but by how fast its engineers could work. The Bailey system embodied the industrial heart of the American war effort. It was a design that reduced the art of bridge building to a repeatable process, one that could be taught, memorized, and executed anywhere in the world. It represented the triumph of process over improvisation, of logistics over landscape. Every bolt tightened under the reign of France or the shellfire of Germany reaffirmed the same idea. Progress was not to be halted by terrain. The army could lose a bridge in the morning and rebuild it by nightfall. And as long as a Bailey set remained on the truck, the road ahead was never truly broken. The true test of the Bailey Bridge system came in the final months of the war, when the Allied armies reached the western bank of the Rhine River in March 1945. The Rhine was more than just a river. It was a symbol of Germany itself, a natural barrier that had protected its heartland for centuries. The German High Command had prepared for this moment, destroying every bridge from Cologne to Koblenz in an effort to halt the Allied advance. For the first time since D-Day, the U.S. Army faced a geographical obstacle that could genuinely slow its momentum. The Rhine was wide, fast, and heavily defended. To cross it under enemy fire required not only courage, but engineering precision on an unprecedented scale. The opportunity came at Remagen. On March 7, 1945, units of the U.S. 9th Armored Division captured the Ludendorff Bridge, one of the last intact crossings over the Rhine. It was a stroke of luck that stunned both sides. The Germans had failed to demolish the bridge completely, and within hours, American forces were streaming across. The bridge, built in 1918 for World War I, was never meant to endure such punishment. Continuous shelling, air raids, and the constant passage of vehicles strained its structure to the breaking point. U.S. engineers raced to stabilize it with timber supports and steel braces, but the damage was already severe. On March 17, after 10 days of desperate effort, the Ludendorff Bridge finally collapsed into the river. Yet by that time, the engineers had already accomplished what no one thought possible. They had established a permanent bridgehead on the east bank of the Rhine. The collapse did not slow them down. Even before the Ludendorff Bridge fell, American engineers had begun constructing alternative crossings. The 291st Engineer Combat Battalion, the 51st Engineer Combat Battalion, and other units under the 1st Army Engineer Command worked around the clock to build pontoon and Bailey bridges just upriver and downriver from Remagen. Working under constant artillery fire, they used the same modular panels and floating supports that had carried them across France. The first new Bailey pontoon bridge was completed by March 10, only 3 days after the initial capture of Remagen. The second followed shortly afterward. Each of these bridges became a lifeline. Over them flowed thousands of trucks, tanks, artillery pieces, and ambulances. Supply convoys moved without interruption, delivering ammunition, fuel, and reinforcements to the units expanding the bridgehead on the east bank. Reports from the U.S. Army Corps of Engineers recorded an astonishing volume of traffic. Over 25,000 vehicles crossed the Rhine each day at Remagen alone. Despite enemy attempts to shell or bomb the crossings, the bridges held firm. Their modular design allowed damaged sections to be replaced within hours, and the crews worked tirelessly to keep the traffic moving. The Bailey Bridge system had proven its full combat value. What had once been a theoretical design for rapid assembly had become the backbone of a real invasion across one of Europe's most formidable rivers. Engineers learned to adapt to every condition. They reinforced floating pontoons with extra anchoring cables to resist the Rhine's current, adjusted the bridge's alignment to reduce strain, and improvised repairs under constant fire. Even as the river swelled with debris and wreckage, the structure endured. Elsewhere along the Rhine, similar feats were repeated. At Wesel, Mannheim, and Oppenheim, entire Bailey bridges were launched across the river in record time. The 17th Armored Engineer Battalion completed a 1,200-foot floating bridge in just 32 hours. The 249th Engineer Combat Battalion built another under smoke cover to conceal the operation from enemy spotters. These efforts allowed multiple Allied armies to cross simultaneously, overwhelming the last German defenses and hastening the end of the war. For the engineers themselves, these crossings represented the culmination of years of preparation. They had trained in mud and darkness in England, built under fire in France, and now, on the banks of the Rhine, they had achieved the ultimate demonstration of speed and precision. The Bailey Bridge had become more than a tool. It was the embodiment of Allied persistence and industrial ingenuity. As the last columns rolled eastward into Germany, the river that had once divided Europe now carried the unmistakable rhythm of progress, measured not in explosions, but in the steady hammering of steel panels and the roar of engines crossing to victory. When the war in Europe ended in 1945, the Bailey Bridge was no longer just a tool of combat. It had become a global symbol of reconstruction, mobility, and modern engineering. What had started as an emergency measure for armies in motion evolved into a blueprint for rebuilding entire nations. Across the shattered landscape of Europe, where thousands of permanent bridges had been destroyed by bombing or demolition, the Bailey system provided a ready-made solution. Within weeks of the German surrender, British, American, and French engineers began using leftover wartime bridge sets to reconnect towns, restore railways, and reopen vital transport routes. The same steel panels that had carried tanks over the Rhine now carried civilians, farmers, and aid convoys over rivers that divided cities from their lifelines. In France and the Low Countries, Bailey bridges remained in service for years after the war. Many of them became semi-permanent fixtures. In Normandy, a Bailey span installed by the 79th Engineer Battalion in 1944 continued to carry traffic well into the 1950s. Similar examples appeared in Belgium, the Netherlands, and Italy, where local authorities reinforced wartime bridges with concrete abutments rather than replaced them. The modular nature of the design made it invaluable for post-war Europe, which faced acute shortages of materials, machinery, and labor. Engineers could rebuild entire transport networks with little more than surplus steel parts and hand tools. The Bailey Bridge soon found a second life outside Europe. In Asia, the U.S. Army and Allied reconstruction agencies supplied Bailey components to Japan and the Philippines as part of their rebuilding programs. In India, where monsoon floods routinely destroyed rural bridges, the design proved perfectly suited to emergency replacement. Indian engineers began producing localized versions under license in the late 1940s, and by the 1950s, the Bailey system had become a staple of national infrastructure. In fact, India continues to manufacture and deploy Bailey-type bridges today, particularly in mountainous regions such as the Himalayas and the northeast frontier. The Korean War of 1950 to 1953 marked the Bailey Bridge's return to combat. Once again, it proved indispensable for mobile warfare. United Nations forces, particularly US and British engineer units, relied on Bailey sets to cross rivers like the Nakhtong and the Imjin under fire. The same qualities that had defined the system in Europe, speed, simplicity, and adaptability, made it essential in the fast-moving battles of Korea's shifting front lines. After the war, many of these bridges were left in place, later forming part of the civilian transport network during Korea's reconstruction. Even the Soviet Union, which had initially dismissed the Bailey Bridge as a product of Western mass production, studied captured examples from Eastern Europe. Soviet engineers analyzed their design and adapted similar modular principles into their own tactical bridge systems, notably the TMM, Tyazly Mechanizirovanny Most, series developed in the 1950s. While these new Soviet bridges differed mechanically, they used folding mechanisms rather than panel assembly. Their conceptual debt to the Bailey system was unmistakable. By the 1960s, Bailey bridges had spread to almost every continent. They were used in Africa for road projects, in Latin America for flood recovery, and in the Middle East for military logistics. Many developing countries, unable to afford large-scale infrastructure projects, turned to Bailey kits as a practical and affordable solution. Their portability made them ideal for regions where permanent construction was impossible due to terrain or instability. The Bailey Bridge had transcended its wartime origins. It had become an international standard, an engineering language shared by nations with vastly different resources and goals. From disaster relief to military campaigns, from remote mountain passes to modern highways, its influence persisted for decades. Its endurance spoke not only to the strength of its steel but to the universality of its concept, that progress could be prefabricated, transported, and built by human hands wherever it was needed. The legacy of the Bailey Bridge extended far beyond the rivers it crossed. For the engineers of the Axis powers who witnessed its rapid deployment during the war, it represented a new philosophy of engineering, one that overturned centuries of tradition. German and Japanese engineering culture had long prized permanence, precision, and aesthetic strength. Bridges were meant to last for generations, monuments to discipline and craftsmanship. Yet, in the collapsing order of 1944 and 1945, such ideals offered no protection against an army that valued adaptability over perfection. The Bailey Bridge embodied a different kind of genius, one rooted in standardization, simplification, and speed. To many European engineers, the contrast was humbling. The Wehrmacht's construction battalions had built magnificent permanent bridges earlier in the war, steel arches, reinforced concrete spans, and rail crossings designed to endure bombardment. But those same structures took weeks to build and only minutes to destroy. The Allies, by contrast, seemed to treat bridges as disposable instruments. They could be built, dismantled, and rebuilt in rhythm with the Army's advance. This philosophy reflected a distinctly American approach to war, an industrial mindset applied to the battlefield. Factories in Detroit and Pittsburgh turned out tanks, trucks, and bridge panels with the same logic of mass production. Each piece fit into a larger system, and that system could be reproduced anywhere, anytime. The Germans had measured engineering success in precision and endurance. The Americans measured it in tempo. In this difference lay the deeper meaning of the Bailey Bridge's legacy. It symbolized the transformation of engineering from a craft to a process. The bridge was not a singular creation but a repeatable event, a formula that could be executed by trained teams with minimal improvisation. What mattered was not the beauty of the structure but its immediacy, its ability to exist exactly when and where it was needed. This industrialization of engineering reshaped military doctrine and civilian construction alike. After the war, American engineers brought home the lessons of modularity and logistics. The same principles that had made the Bailey Bridge possible influenced post-war infrastructure programs, the prefabricated housing projects of the late 1940s, the rapid expansion of highways in the 1950s, and even the standardized architecture of military bases during the Cold War. The bridge's philosophy, build fast, build modular, build to function, became part of the modern American identity. For the Axis engineers who studied captured Bailey sets after the war, the message was unmistakable. Strength was no longer defined by mass or monumentality, but by the ability to respond. In the ruins of Europe, the most enduring legacy was not concrete, but flexibility. The Bailey Bridge taught that resilience came from systems that could adapt as quickly as circumstances changed. This was a revelation to traditions that had equated durability with dominance. The deeper reflection of this legacy lay in its human dimension. The Bailey Bridge was not only a triumph of design, it was a triumph of coordination, cooperation, and collective purpose. Thousands of soldiers, most with no formal engineering background, learned to construct complex structures under fire. Each bridge represented a union of intellect and labor, of planning and courage. It was proof that in the chaos of war, order could still be created through discipline and shared understanding. By the end of the 20th century, the Bailey Bridge had come to represent something larger than military ingenuity. It stood as a metaphor for the century itself, a world rebuilt not by monuments but by systems, not by permanence but by motion. Its simplicity became its strength, and its reproducibility became its immortality. In a war that had destroyed so much, the Bailey Bridge left behind an idea that endured, that progress is not a matter of building what lasts forever, but of building what can begin again. The story of America's wartime bridges was, at its heart, a story about a new kind of power. It revealed a civilization that no longer measured strength through conquest or monumentality, but through its ability to move, rebuild, and connect. In an era defined by destruction on an unprecedented scale, the United States had turned engineering into a moral act, the assertion that creation could outpace ruin. The Bailey Bridge stood as the clearest expression of that belief. It was not a monument to victory, but a testament to continuity, to the idea that the will to rebuild was stronger than the impulse to destroy. Where the old world had placed its faith in permanence, in walls, fortresses, and fixed lines, the new world placed it in motion. The Allies did not seek to hold ground through immovable structures, they advanced by building the means to keep moving. The Bailey Bridge embodied this transformation. It was born not from a vision of grandeur, but from the logic of resilience. Each bridge was temporary, yet its impact was lasting. It existed for days, sometimes only hours, but in that short span it carried armies, supplies, and the weight of a civilization determined to push forward. To observers of the time, these structures symbolized more than tactical ingenuity. They marked a philosophical shift in how humanity confronted adversity. The 20th century had begun with empires that built in stone, confident in their permanence. It ended with societies that understood impermanence as a condition of survival. The Bailey Bridge captured this evolution. It was a structure that accepted its own fragility but drew strength from repetition and renewal. Every time one fell, another could rise. The very act of rebuilding became a form of defiance against despair. For the American engineers who assembled these bridges under fire, the work carried a quiet significance. They were not sculptors or architects, yet their labors shaped the moral landscape of the war. Each bolt tightened and each panel raised was a rejection of paralysis, a refusal to let destruction dictate the rhythm of history. To build in a world consumed by ruin was, in its own way, an act of hope. After the war, as these bridges found new lives across Europe, Asia, and beyond, their meaning deepened. They connected not only rivers but nations, serving communities that once faced one another across battle lines. They became instruments of recovery, symbols of how technology, when guided by human purpose, could heal the wounds it once helped inflict. The Bailey Bridge was no longer simply a tool of war. It was an emblem of reconciliation, proof that the same ingenuity that sustained conflict could also sustain peace. In the ruins of the 20th century, the Bailey Bridge offered a simple but profound lesson. Power was no longer the ability to dominate or endure unbroken, it was the capacity to rebuild. The strength of a society lay not in the permanence of its walls, but in the speed with which it could restore what had been lost. America's engineers had built more than crossings. They had built a philosophy of movement, adaptability, and renewal. Long after the last shots of the war faded, the silhouette of the Bailey Bridge remained etched in history as a quiet monument to persistence. It spoke of a truth learned in the hardest years humanity had ever faced, that progress endures when people refuse to stand still. Destruction was temporary. Motion was eternal. And in that motion, between the banks of rivers and the turning of time, lay the enduring bridge between survival and civilization.